I'm often asked in the comments of my videos how to do 2D rendering using C++. In this video, we'll create a basic animation from scratch and cover all the steps, from installing the necessary tools and libraries to the implementation. This simple animation of an infinite journey among the stars will allow us to cover some of the key concepts of rendering. We're going to start from a blank virtual machine to put ourselves in the situation of someone who really has to start from the very beginning. First, we'll need a toolchain to compile our code. The easiest way to do this on Windows is to install Visual Studio. It seems that the installer interface is completely broken. For what we want to do, we need to select Desktop Development with C++ and tick the command line interface Build Tools item. Next, we'll need to install Git, which is the standard for code versioning and is required to interact with GitHub. If you're new to all this, I'd advise you to learn a bit about Git and its ecosystem, because it really is a central tool in software development. We can check that the installation has worked by running Git in a terminal. Finally, we'll install CMake, which allows to configure and generate a C++ project ready for compiling. Like Git, it's an essential tool for C++ projects, and it's worth knowing a little about it. We can also quickly check that the installation has been successful using a terminal. Now that we've got all the tools we need, let's see how to compile code to draw things on screen. For this project, we're going to use the SFML, which to my knowledge is the best C++ library to easily do 2D rendering. It has its limitations, but allows you to get very far before turning to much more complex alternatives. And it's backed up by impeccable documentation and a series of clear, detailed tutorials. For me, it's the ideal gateway to C++ rendering and game development. A CMake template is also available on GitHub for quick and easy use in our projects. We're going to retrieve the URL from the repo and then import it locally using Git. To obtain the code, first go to the location where you want the code to be copied. Then use the command git clone, followed by the URL of the repo. This will download the code and configure the repo. We'll then create a build folder inside it, containing all the files related to the project's configuration and compilation. These files will be generated when executing this command that will tell CMake to configure the project using the CMake lists text file present in the parent directory. CMake can generate projects for a wide range of toolchains, but will use Visual Studio on Windows by default. Executing this command may take a little time, as it will locally install the SFML so that it can be used for the project. In this case, locally means that the installation will only be effective for this project. Once configuration is complete, we can have a look at the contents of the build folder, and we can see that CMake has done its homework. In particular, it has created a Visual Studio solution that can be opened. From here, we can easily compile the project. The first compilation will take longer, since SFML will also have to be compiled. Future compilations will be much faster. If all has gone well, once compilation is complete, you can run the project and an empty window should appear. To push the test a little further, let's add a green disk. This small modification will ensure that auto-completion works properly and will help us appreciate the simplicity of this library. As expected, we can see that compilation is much faster this time. I'll quickly present an alternative procedure using CLion, which is an IDE I use on a daily basis and which has excellent CMake integration. Unfortunately, CLion is not free, unless you are a student. Personally, I find it much more enjoyable than Visual Studio. To create a project from a repo designed for use with CMake, simply right-click and select Open Folder as CLion project. CLion will automatically call CMake in the background and configure itself accordingly. When we first open the project, we're asked to choose which compiler to use. As Visual Studio is installed, I'm going to use the toolchain that comes with it. You can then directly compile and run the project. We can run a small test like before to check that everything is in order by modifying the code slightly. For example, by turning the disk red. Now that everything's working, let's create our own project. Using the CMake file supplied with the template. I'll be using CLion for the rest of the video, but the principle is exactly the same for Visual Studio. We'll start by copying the CMake configuration file from the template project into a new folder. With CLion, I add a release configuration when the project is initialized, but this is not necessary with Visual Studio, which will create it automatically when the solution is generated with CMake. If we try to generate the project directly with CMake, which CLion does here on its own, we'll get an error. The reason is that the template file expects to find a src folder containing a main CPP file. The configuration file can be customized, which is what I'm doing here to change the name of the project and the executable that will be generated. But it's perfectly possible to keep the file as is. Next, let's create the missing file in a src folder. It's perfectly possible to choose another structure, but here we'll keep the same one. We can use the template's main function as a starting point for our project. Then, I add the ability to exit by pressing escape, which is very practical when the program is in full screen mode and we no longer have access to the window buttons. To keep the main function as clean as possible, I prefer to move the events management to another file. To be included in the compilation, CPP files must be added to the list of sources in the CMake configuration file. Again, this is something CLion does on its own, but generally speaking, simply add the file here. Next, I create a configuration file containing all the program constants. On the one hand, this avoids having too many magic numbers everywhere, and on the other, it makes it easy to modify parameters. I also create a float version of the window size, which is usually quite useful later on, especially when the scene is the same size. Now that the main function is ready, let's create the structure of our stars. In our case, a star is simply defined by a position on the screen and a depth on the z-axis. The stars will then be stored in a vector initialized in this function. Here, I use a more robust method than simple rand with a modulo to obtain pseudo-random numbers. To begin with, we're going to draw the stars using disks. This is very easy to do with SFML. We'll start by defining a circle shape object, which is initialized with a radius. To ensure that the disk is centered at the star's position, we'll move its origin to its center. We'll then position the disk at the coordinates of each star and draw it in our window. And just like that, we get our 1000 stars. For a more immersive rendering, let's switch the display mode to full screen. Next, let's see how we can add the illusion of depth to our scene. We'll need two new constants, the near and far distances, which respectively define the minimum and maximum value Z can take for our stars. Each star will then be assigned a random depth within this interval. We can use this value to define a scaling coefficient equal to the inverse of the depth. In other words, the larger the depth, the smaller the scale, and vice versa. This is quite intuitive, because the further away objects are, the smaller they appear and the more they converge towards the horizon. Position and radius of the disks are then multiplied by this scale factor before they are drawn. The result is a little strange. What happens is that the default origin is the top left corner, so all positions will converge towards it. To solve this problem, simply generate random positions around 0 and then translate them to the center of the window. That's much better. Now let's add a forward travel effect. We'll simply linearly decrease the value of Z for each star. To do this, we'll subtract the speed multiplied by dt to make the displacement frame rate invariant. It's not too bad, but there's an annoying problem when Z goes negative. A very simple solution is not to draw the stars that have passed behind the camera. To add a depth effect, we make distant stars darker by multiplying the color by the depth ratio. The effect isn't too bad, but a problem is now becoming apparent. Some distant stars are drawn on top of closer ones. And that's not very surprising. Depths are random, so there's no guarantee that distant stars will be the first in our vector. To correct this, we can simply sort the stars by decreasing depth, so that those furthest away are drawn first. It's a costly operation, but as we only have to do it at initialization stage, it's not a real problem for performance. The problem is solved and the rendering is not too bad. However, we quickly run out of stars. We could simply add more, but the easiest thing to do is to reuse the ones that are no longer visible. To do this, we'll simply send the stars behind the camera to the back of the scene. We do indeed have infinite stars, but we come back to the problem of drawing order. We could simply resort our vector each time, but fortunately there are much simpler ways. In fact, the star cycle remains the same. What changes is the starting point. We can therefore define an offset equal to the index of the star we've just sent to the back, since we know it's the furthest away. The visibility test is no longer necessary, as this case is handled above. At first glance, this solution seems satisfactory, but if we render with 10,000 stars, we can clearly see that there's a problem with some objects being briefly drawn on top of others. The problem here is a little more subtle. Normally, when a star is sent back, there is no hitch. The starting index is correctly updated. However, at the same tick, two stars may pass behind the near plane. In this case, the new starting index should be that of the nearest object. In this case, index 8. But since iteration is from farthest to nearest, in the current code, index 9 will be processed last and will have the last word for the final value of the starting index. The simplest solution is therefore to update objects from front to back, which naturally solves the problem. At last, everything is working properly. However, the rendering isn't very convincing because the stars don't fill our field of view. To remedy this, we can simply scale the area in which the coordinates are generated so that it fills the screen. Here, for all the stars to fill the visible space, they would have to cover the far plane, so we'll scale the zone by the far value. The solution is a little brutal, but the illusion of space is much better. On the other hand, something I find particularly unpleasant are all the stars that suddenly disappear right across the screen. To solve this problem completely, we'll simply define a zone where there will be no stars. This zone corresponds to the window size scaled by the near value. It's not a very elegant way of doing things, but then again, it doesn't affect performance, so we won't spend too much time on it. We no longer have the original problem, but the effect isn't exactly subtle. To make the area less perceptible, we can simply bring the near plane closer, thus greatly reducing the size of the projected area on the far plane. The area is now imperceptible. However, there's one aspect I've totally ignored here: performance. With 100,000 stars, performance is truly abysmal. The first thing to do in this case is to make sure that the program is compiled in release mode, which activates optimizations and can boost performance dramatically. Here, we go from 13 to 31 frames per second, which is a good improvement in itself, but still very poor. The problem really lies in the way the rendering is done. Calls to the draw function, generally referred to as draw calls, are quite costly and can severely affect performance. For best optimization, it's very important to use as few as possible. In our case, we can use just one and draw all the stars at once. To do this, we're going to use vertex arrays, a very powerful feature of SFML. It lets you manually specify, in a large array, the characteristics of the vertices that will make up our entity to be drawn. They are defined by the way the vertices are assembled, and a size. Here, we want to draw quads, so we'll use the appropriate primitive type and have 4 vertices per star. It's a little more complex to draw this way, so it's cleaner to create a function dedicated to updating vertices. One advantage of doing it this way is that vertex array updates can be very simply multi-threaded, if needed, as each star is independent. To translate all the vertices at once, simply pass a transformation matrix as an argument to the draw function. Let's take a look at the performance offered by this new approach. The increase here is spectacular. Out of curiosity, let's see how far we can go before we drop below 60 frames per second. Thanks to vertex arrays, we can now display 1,000,000 stars at 60 frames per second, without multi-threading. This technique is the ideal choice for drawing large numbers of objects on screen. We're not quite done yet though. We don't want white squares, we want stars. To achieve this, we're going to use a texture that will apply to the quads. I usually place all my textures in a res folder and define a small script in CMake that automatically copies this folder next to the generated executable. But this can be done very well by hand. Loading a texture with SFML is extremely simple. It supports a wide range of image formats and, as always, provides a comprehensive and consistent interface. For the texture to be displayed on quads, we then need to define which part of the texture each vertex will be associated with. This usually only has to be done once. For the vertex array to be drawn with the texture, we must use a renderStates object, which groups all the information associated to the draw call. Here, we specify a transformation and a texture. And here are our quads, now properly textured. I prefer to hide the mouse in this kind of projects, which is fortunately very easy to do. I'm also taking the opportunity to make the stars a little bigger. And here's the final result. I hope this introductory video about C++ rendering with SFML will help. I'm planning to make more videos on this subject, especially about how I program my graphical interfaces.